Hi, my name is Adrian, and in this tutorial video I'm going to show you how to use one of the functions of the influential R package for the visualization of a network based on the centrality of nodes. And by centrality I mean every kind of centrality. For example, you may desire to apply degree or between a centrality or neighborhood connectivity or whatever kind of actually centrality measure that you would like to apply on network nodes to demonstrate which nodes are more important in the context of that specific centrality measure. But for the sake of this tutorial video, I'm gonna using IVI, or the integrated value of influence, which is sort of a novel centrality measure that we recently developed for the identification of the most influential nodes within a network. So let's kick it off, and we first load the influential R package and we set the seed to 70 or whatever kind of seed that you would desire, but for reproducibility we set the seed to 70, so that if you set the seed 70 in your R environment, you would get the same results that I'm generating right now. So we first use one of the functions of the R package iGraph for generation of a random network that includes 50 nodes and 120 edges, and we set directed to true so that the network is reconstructed as a directed network. We then use the IVI function from the R package influential for the calculation of IVI values of all of the nodes within the network. And at the end, we use another function of the R package influential named sendNetworkWiz, which is actually the focus of this tutorial video for the visualization of network based on IVI values. And as you can see, we have inputted only two arguments, graph and sendMetric. The graph is actually the graph that you have generated. You can use also different functions of the R package influential for generation of a graph from an adjacency matrix or data frame or some other data types according to your input data. But for now we use the same graph that we recently generated, and we use the IVI values that we calculated in the previous step. And let's have a look at the results. And yes, as you can see, a figure has been generated, which is quite beautiful and almost ready for publication. And as you can see, the node size and the font size of labels and also the node color is all of them are proportional to the IVI value. But it is not the end, and a complete flexibility has been provided for the optimization of all of the visual features of the network. So let's have a look at the help page of the function, and as you can see, a list of different arguments have been provided for the adjustment of visual features. So let's start with the layout. And if you scroll down, you see that a wide range of different layouts have been provided so that you can set on the plot to get a different visualization. But for now we can use, for example, an automatic layout, which automatically applies a layout to the network based on the structure of the network. And as you can see, it is not that different. The default layout is KK, and it is not that different from the automatic layout, but we will continue with the default layout. And the next one is node color, and different options have been provided to set the node color. So let's change it to magma, for example. And as you can see, the node color has changed. And the next argument is node min size and node max size. And the min size by default is set to 3 and the max size by default is set to 15. So let's change it to 1 and 20, for instance, and see what will happen. And yay, as you can see, the nodes with lower IBI values are smaller, and the nodes with higher IBI values become bigger, so that they are more distinct from the rest of the nodes within the network. But we will keep them to default. And the next argument is dist power. And the dist power, let's go to the help page. The dist power is actually the power to be used to visualize more distinction between nodes with higher and lower centrality measure values. And the higher the power, the smaller the nodes with lower values of the centrality measure will become. And the default is set to 1, so that no distinction power is applied to the network. As you can see, it is the original network. But for the sake of visualization, you may apply, for example, a distinction power of 2 or whatever you would desire to actually apply a more, distinction between nodes with higher, IBI values or whatever kind of centrality measure that we have used, and the nodes with lower IBI values. And let's continue with, again, the default option. And the next option is a node shape. You can apply different shapes like diamond, triangle, or square for the visualization of actually network nodes. So let's change the network node shape to diamond, for example. And as you can see, all of the nodes have changed. But if you look at the help page of the function, you see that it is also possible to provide a character vector for the node shape with the same length as the number of nodes within the network to actually visualize different nodes with different shapes. Suppose, for example, you are reconstructing a network that includes both proteins and RNAs, and you would like to visualize RNAs with a specific shape and proteins with another shape. So for now, let's just simply provide a character vector that includes 25 nodes or 50% of nodes as diamond, and another 25 or another 50% of nodes as circle. And as you can see, 50% of nodes have been adopting a circle shape, and the other 50% have a diamond shape. And you should note that the order of this character vector should actually correspond to the order of nodes within the network. And if you would like to see the order of nodes within the network, you can just use one of the other functions of the R package influential, which has been adapted from iGraph package to see actually the order of the network nodes. So if you just use the function v for vertices and input the graph, you would get the name of nodes and their order within the network. So for now, because the nodes, the actually graph has been generated as a random graph, all of the nodes have numbers as their names or labels, and they are ordered. But if you have I don't know, a regulator network of genes, you can get the name and order of vertices using this function. So the next argument is stroke size, and as you can see, there is a border around each of the nodes within the network, and it is by default set to 1.5, but let's set it to 3. And see how it is changed. And as you can see, the size of stroke or border around the nodes has increased. The next argument is stroke color, and again you can set the stroke color. For example, let's set it to orange, and the stroke color of all of the nodes would get changed. But it is also, again, similar to node shape, it is possible to provide a character vector of different colors based on actually the characteristics of different nodes within the network. Suppose, for example, you are reconstructing a network that includes differentially expressed genes, and some of the genes are upregulated and the others are downregulated. So you would apply red, for example, to upregulated genes and blue to downregulated genes. So it would be possible just by providing a character vector, and again you see that the color is applied to a stroke color of nodes. And the next argument is stroke alpha, which indicates the transparency of border around the nodes. You can make it solid. By default, it is set to 0.6. But as you increase the value of stroke alpha, the border color would become more solid, and as you decrease the stroke alpha, it would actually become more transparent. The stroke color would become more transparent. The next one is show labels, and if you set it to false, the actually labels of nodes are removed from the network. And the next one is label 6, that corresponds to the font size of labels within the network, and it is by default set to 0.4. And if you increase it, the size of labels within the network is increased, but proportionally to the actually proportional to the IVI values, and based on the IVI values, different nodes would get different label sizes. And the next one is label color. You can also change the color of labels within the network. It is by default set to black. And the next argument is directed, and if your network is directed, which is the case for this tutorial video, you can set it to true, so that the network would be visualized as a directed network. And the next argument is arrow width and arrow length, and again you can change the size of arrow within the network if you have set the directed to true. And the actually next argument is edge width, and you can change the width of edge within the network. It is by default set to 0.5, but let's change it to 1, and as you can see, the width of edges within the network is increased, but let's keep it to the default. And the next argument is weighted, and if your network is weighted, you can set it to true. By default it is false. And if your network is weighted, then you would choose the edge width min and edge width max to set the min and max of edge within the network based on the weight of connections. And the next argument is edge color. You can change the edge color to whatever kind of color you would desire. It is by default set to gray 75. And you can also change the edge line type. Range of different line types are available. For example, long dash, dot dash, dotted, or dashed, or solid. So let's change it to dashed, for example. And as you can see, the edges are changed from solid to dashed. And the next argument would be legend position, and by default it is positioned in the right side of the graph, but it is possible to put it on the left, bottom, or top of the graph. And the other argument is legend direction. By default it is vertical, but you can set it to horizontal, especially when you are putting this to the top or bottom of the figure. And the next one is legend title. By default it is centrality measure, but as we are actually generating the figure based on IVI values, we can set the legend title to IVI value. And the next argument is box legend, and as you can see, there is a box around the legend. By default it is set to true by default, but you can change it to false so that the box is not drawn around the legend, but we will keep it to true for now. And the next argument is show plot title, which indicates whether to show the plot title or not. It is by default set to true. We will keep it to true. And the next one is plot title, and by default the title is centrality measure based network. You can change it to whatever kind of title you would desire. So let's change it to IVI based network. You can also change the title position. It is by default in the center of the figure. You can change the title position and put it, for example, to the left of the left side of the figure. And the next arguments are actually show bottom border and show left border. And as you can see in the current figure, we have the bottom border and left border, but if you would desire, you can remove the bottom border and left border, but by setting the show bottom border and left border to false. and yeah, it's done. But for the last point, sometimes the network is so crowded, and think about the situation that you are reconstructing a network that includes maybe 100 or 200 nodes, and in such situations the network, uh, if you apply the default layout, some of the nodes would overlap each other, and the network would not be clearly seen, and the actually nodes with different IVI values, different centrality measures would not be clearly separated from each other. So let's see what will happen. Let's set the number of nodes to 100 and the number of edges to 250, for instance, and let's set the seed again and reconstruct the network and calculate the IVI. And because the number of nodes have changed, we set it to, now we have 100 nodes, so we should change them to 50 different shapes and different colors all together should have the same length as the number of nodes within the network. So let's generate the network again and see how it looks like. And as you can see, some of the nodes overlap each other, and for such situations I would recommend, maybe the best layout would be a grid layout. So let's again have a look at the results, and as you can see, it is much more clear that which nodes are more important within the network based on the centrality measure that you are using. So in the situations that you have a really crowded network, I would recommend use a different layout like grid, which arranges all of the nodes in a way that are clearly separated from each other. And that's it. Enjoy your visualization.